Here's the final assembly, analog to digital converting, and shift add 3 output. This project is divided into 3 parts. The timer 1 triggered ADC conversion, the shift add 3 algorithm converting the ADC output to binary converted decimal, and the serial transmission. Though serial transmission is the last step, we'll start with the serial setup. Using the USART chapter within the ATML 328P datasheet, it's relatively easy to get it working. The first thing you'll note is that there are 4 types of clock generation, and these are different ways a serial monitor can be used to communicate. For our purpose, we'll use normal asynchronous mode. If you're curious about the modes, here's a brief overview of the differences between. Next, to determine our baud rate, we use this formula, where we ultimately have our USART baud rate register, UBRRN, constant set to 103, as it gives an approximate baud rate of 9600. To actually set this baud rate, we need to put the value, 103, into the UBRR high and low registers, where we take the high byte of the baud prescaler, 103, load it into the high UBRR byte, and do the same for the low byte. Next, given the USART control and status register B table, we can determine we need to write a high to the TXEN 0 bit, which will turn on serial transmission. Lastly, we have to set the clock operation to normal asynchronous, and we also have to set the parity and stop bits. Given the table below, we can determine we want to write 0 to bits 7 and 6 for normal asynchronous. Then, we'll write a 0 for bits 5 and 4 since we don't need parity. We'll set bit 3 to 0 for one stop bit, and lastly we'll set the character data size per frame to 8 bits by writing 1 to bits 2 and 1. All of this is then loaded into the USART control and status register NC. The next step will be setting up the internal 10-bit successive approximation analog to digital converter within the Nano. I'm not going to go into every step in depth, but the same process of reading the datasheet to set up the serial communication can also be done with the analog to digital converter. I will highlight one important note, which is that we'll set the ADC trigger source to a timer 1 overflow, which can be done by writing 110 to bits 2, 1, and 0 respectively in the ADC control and status register B. Now, I'll talk about the ADC vector interrupt. This interrupt is triggered every time an ADC conversion is complete. First, there's a toggle on pin 13 causing it to blink on the Nano. And next comes the shift add 3 algorithm. The purpose of the shift add 3 algorithm is to convert a binary number into binary converted decimal, which basically means that each nibble represents a different binary digit. The purpose of BCD is to allow us to print out the ADC output in decimal on the serial monitor. Here is the basic bit outline for the shift add 3 algorithm. The rightmost BCD nibble is the ones digit and the leftmost BCD nibble is the thousands digit. The ADC result will then be stored in bins 1 and 0. So to start, all BCD bytes are cleared, as from the previous conversion they would have been filled with the last BCD value. Then, since the ADC has just been complete, the ADC result can be loaded into bin 0 and bin 1 with LDS, load direct from SRAM. It's crucial to note that the lower byte must be loaded before the high byte, or else the low byte will be discarded. Next comes the double-dabble algorithm. This algorithm has 2 parts, the shift and the add 3. The shift is simple. It's just everything from the given bit outline once left. It starts with an LSL, logical shift left, on the rightmost byte, bin 0, followed by a roll, rotate left through carry, on all other bytes from right to left. Before each shift, however, a check is done to see if any BCD nibble is storing a value of 5 or greater. If it is, then a 3 must be added to that nibble. That's how the check algorithm works. It starts at the ones digit nibble, loads the first BCD byte into a general purpose register, masks the lower nibble, then compares a constant 4 with a lower nibble value. If the comparison of 4 minus the lower nibble value is positive, then skip what follows and branch to check nibble 2. This is done with the branch if plus instruction. If the end flag is triggered, however, then a hex 3 will be added to the lower nibble. Then we'll go to the check nibble 2 process. The check nibble 2 process is nearly identical, except the low and high nibbles are swapped before the mask is done. Then instead of a hex 3 added, a hex 30 is added to the byte. This process repeats for the third and fourth nibbles. After the shift comes the completion check, where once bin 0 and bin 1 are completely empty, the double-dabble algorithm is complete. This is done by ORing bin 0 and bin 1 in a general purpose register, then testing for 0. If not 0, then repeat the check and shift. Once the BCD value is complete, the display function is called, which isolates every digit one by one and prints it out on the serial monitor.